In this video, I'm going to talk about ionic bonds and how you show ionic compounds using Lewis structures. Before we get into bonds, we need to cover a basic rule, and that is, why do atoms form chemical bonds anyway? Why do chemical compounds form? Well, in general, chemical bonds are designed to provide each atom with 8 electrons in the highest energy level. That's known as an octet. You can see like octopus, it means 8. So the atoms come together in ways that allow every atom present in that compound to have access to 8 electrons. Our noble gases already have 8 electrons in the highest energy level, or in the valence level. And so we have neon over here as a model, and you can see in that outermost ring of our Bohr model of neon, we have 8 electrons present. And that's really why those noble gases are not going to react with any other elements under normal conditions. You can force them to do things in a laboratory, but that's not natural. Metals tend to give up electrons when they're forming bonds, and nonmetals tend to accept electrons if they're forming an ionic compound with a metal, or when two nonmetals come together for a covalent compound, they tend to share the electrons between the atoms. Incidentally, hydrogen, which is in that same row as helium, is stable with only 2 electrons. It doesn't have room to hold 8 electrons, so it's happy if it just gets 2. So whenever you're thinking about bonds, whether ionic bonds or covalent bonds, this octet rule, looking to make each atom have 8 electrons available to it, is the way to go. So let's talk about ionic bonds. Typically, ionic bonds are formed when you have a metal and a non-metal forming a compound. And the atoms in this compound exist as ions because electrons have moved. That's the key word for ionic bonds. Electrons have up and left one atom and gone to live with another atom. And in doing so, they form octets in the valence electrons, or in the last energy level present is going to have 8 electrons. We use the word ionization energy to talk about how much energy it takes to give up an electron. And so atoms that have low ionization energies are ones that are going to more easily give up electrons. You see by this diagram that ionization energy is low towards the left of the periodic table and towards the bottom left-hand corner. So the atoms that tend to give up their electrons most easily, the most reactive metals, are the ones down here in the bottom edge. The very, very bottom, francium, is not particularly common in nature. Then the other side, the ability to attract electrons, has this name electronegativity. And so atoms that have a high electronegativity more easily attract electrons. Where do we find those? Well, those are found, aside from these noble gases that don't count, but they're found over here on the right-hand side of the periodic table. In fact, that upper right-hand corner, where you have things like oxygen and fluorine. Those are very, very reactive nonmetals. They like to react, they like to grab electrons and pull them off of metals. So let's just use sodium chloride as a familiar example. The ionic compounds that are going to form as these ions are made are being held together by attractive charges, by those positive and negative charges, because these opposite charges attract. So here's our sodium atom. It originally has 1 valence electron in the 3 energy level. It's because sodium is found on the 3rd row of the periodic table. This electron is attracted to, it is given up by sodium and taken in by chlorine, joining the 7 valence electrons already present on chlorine to make 8. So as a result, sodium, having lost an electron, gains a positive charge of 1, because 1 electron moved, and chlorine becomes the chloride ion with a negative 1 charge because it has added 1 more electron to its neutral state. And it is these positive and negative charges that cause the attraction and help hold sodium and chloride together as this sodium chloride compound that we're very familiar with. Because the ions have this charge actually in all directions, so our little chloride ion here in the corner of this diagram, is giving off negative charge to the right and the left and the top and the bottom. It's negative everywhere. And so ionic compounds are not just a singular molecule consisting of only 1 atom of each charged particle, in the case here of sodium chloride. It's not 1 sodium and 1 chloride put together, but the negative ions or the positive ions will attract as many other ions as present and to form these things called crystal lattices, where the atoms are tightly bound together, where every negative ion has as much positive ion attracted to it as possible given how many atoms are present. Every positive ion has as much negative ions around it as possible given how many atoms are present. And so that gives our ionic compounds certain characteristics, one of which is that they often form crystals. And the shape of the crystal will depend on how the atoms, the positive and negative charges, line up. For example, we have sodium chloride here, which is a 1-to-1 ratio. So, the formula is NaCl. But the other example over here, calcium fluoride, is actually going to be a CaF2. So you're going to have two fluoride ions tight around every calcium ion. Crystal lattices typically show a cube structure, a six-sided structure where you have a repeating pattern, and so that's what they're showing here with these lines kind of superimposed on these diagrams. They're trying to outline the cube for each of these. Ionic compounds also tend to have high melting and boiling points, so they tend to be solid in most of our everyday temperatures. They are hard and brittle, and when they are dissolved in water, or if they're even melted, if you do have a high enough temperature, they will conduct electricity because those ions are able to carry the electric charge. So if you want to show an ionic compound using a Lewis structure or a Lewis dot diagram, there are a couple of things you need to remember. Your metal cation, your positive ion that's going to form, is going to give up all of its valence electrons, gaining a positive charge because now it has been an imbalance where there's fewer negative electrons as compared to positive protons. It will drop back to the next energy level and have a full shell there, but we don't show those electrons in our Lewis structures. To do the Lewis structure, you're going to write the atomic symbol and show no valence electrons, even though electrons are present. You would put square brackets around the symbol and then write the charges present outside the brackets. The negative nonmetal, the anion, will gain electrons until it has an octet. So however many spaces need to be filled until you make it to those 8 electrons, or how many are going to be filled in an ionic compound. And the negative charge will then be appropriate to how many extra electrons have been added. In writing your nonmetals or your anions, you do your atomic symbol and show all 8 valence electrons. So you don't show any electrons on the positive ion, you do show all 8 electrons on the negative ion. You put square brackets around the symbol and the electrons and put the charge on the outside of the brackets. So let's do a couple of examples to just show you how. So consider potassium and chlorine. So I've already drawn the Lewis structure. Potassium has 1 valence electron and chlorine has 7. So this 1 valence electron is going to be off the potassium, is what's going to move. It'll move, I don't have this very well set up, it's going to move all the way over here to fill in this spot when we form an ionic compound. So to write the Lewis structure for potassium chloride, we first write our atomic symbol for potassium. Put it in square brackets. I'm not going to show any valence electrons. I'll just put the charge on the outside. Then we do chlorine, as a chloride ion is going to have 8 electrons around it, and it's going to have that filled octet because that electron has moved. Draw those 8 electrons, put square brackets around it, and write the charge on the outside. So that's all there is to it for doing a Lewis structure for potassium chloride. How about magnesium plus oxygen? Magnesium has 2 valence electrons, and so they both are going to be given away in forming an ionic compound. And thankfully, oxygen has 2 spaces where we could add another electron to make those 8 electrons around oxygen. And so there's going to be a simple movement of the 2 electrons off magnesium onto oxygen. So again, magnesium is going to end up this time with a positive 2 charge, and remember it can be +2 or 2+, and oxygen is going to show those 8 valence electrons around it with that filled outer shell, and again square brackets and a -2 because we've added 2 electrons. So Lewis structure for magnesium oxide. Finally, how about magnesium bromide? magnesium plus bromine. Here you have 2 electrons again for magnesium, but there's only one space on bromine. So one of these electrons can go here, but we have got to get rid of this second electron. So how can we get rid of that second electron? Well, we need another bromide ion in order, or a bromine atom, to accept it and become a bromide ion. And so then this electron can go over here on this second bromine atom and form another bromide ion. So to write out this formula, sometimes you'll see ones written where all of the individual atoms are written out. So you'd write out magnesium and one bromide ion and another bromide ion, but I think it's perfectly fine to just use some coefficients. So we'll do our magnesium. You always write the positive one first. So there's our magnesium ion, and then I'm going to say there are 2 of these bromide ions, and so then we have to show those with all 8 electrons present, put the square brackets around it, and 1 negative because each bromide ion only has a -1 charge, but then the 2 here in front as a coefficient tells you that we have 2 of them. So you want to make sure your charges add up to 0. This is another way of figuring out what the formula is for combining atoms together in ionic compounds, and then use the coefficient to represent that. So that covers ionic bonds. Remember, electrons move so that your metal will lose all of its valence electrons and your nonmetal will gain as many electrons as it needs to make that octet around it. And then when you're writing the Lewis structures, your positive ion will never show any electrons because you've lost all of the ones in the outermost energy level, and your negative ion will always show the full 8 octet, those 8 valence electrons around it.